present this study during 2013. I was working at Kyushu University with Saburo Okazaki, Professor Isao Matsunaga, and Professor Yukitaka Murakami, and we were studying the influence of small tilted defects on the fatigue limit of steels. And after that, I started working here in France, and we did some synchrotron analysis of the non-propagating cracks that we found at the fatigue limit of these steels. So I will briefly introduce the result of Japan, and then I will show the 3D non-propagating cracks analysis. As an introduction, here is the famous Murakami's model, and it relates the fatigue limit of certain steels with the hardness of the material and the square root of area parameter. Here in this equation, area corresponds to the projected area of the defect into a plane normal to the stress to the loading directions. That means that if we have two different defects with different tilting angles, but the same projected area, this material should have the same fatigue limit. And that was the objective of this study. Just clarify if this is okay or not, if material behaves like this. And also characterize the non-propagating cracks found at the fatigue limit. So we choose three different steels. I don't know if you see from there, but the idea was to have a wide range of mechanical properties. We have yield stress of 200, 340 and 750 megapascals. And we prepare the specimens for the fatigue campaign, and then we remove the residual stresses from the surface, and we introduce the artificial defects. These artificial defects were a semicircular slit at 0 degrees, a semi-elliptical slit at 30 degrees, and at 60 degrees. The idea is that if we project the area on the z-axis, we are going to have the same square root parameter, and then we do an extra, the typical Murakami's artificial defect by drilling, and the four of them have the same square root parameter. We did some fully reverse fatigue test at 150 Hertz. The fatigue limit was defined as typical non-failure after 10 million cycles, and we did periodical interruptions in order to measure the crack length. So, I don't know if you can see from there, but this is the typical SN diagrams. In this case was for the third steel, the low alloy steel, the one with higher mechanical properties, but this is not that important. This is a resume of those results. This is the low carbon steel, medium carbon steel, and low alloy steel. In this case, this is here we plot the fatigue limit divided by the prediction of Murakami's model, and we see no influence, and this is 0 degrees, 30 degrees, and 60 degrees. And we observed no influence, or not a big influence of the tilting angle on the fatigue limit of these two first carbon steels. You can see again here that the fatigue limit is within 10% of the prediction of Murakami's model. In the other case, in the third case, in the higher mechanical properties steel, the low alloy steel, we have a clear increment of the fatigue limit with increasing the tilting angle of this artificial defect. So I will present first the first analysis that we did there in Japan was to follow up the crack, and we observed in every material and every defect non-propagating cracks at the fatigue limit. The non-propagating criterion is these cracks. It's not so clear here, but the crack start propagating and propagate for 1 million and then remains without changing the length for 9 million cycles. And we also observe, the non-propagating cracks and the fatigue tests that were done above the fatigue limit has this deceleration of the cracks that reached to a minimum and then started growing again. And this minimum coincides, is really similar with the length of the non-propagating cracks that we found at the fatigue limit. This length of the non-propagating crack, this is the non-propagating crack length, and this is the position of this minimum on the propagating crack. And we can see that they are all really similar. But another thing that I want to show in this graph is that the softer the steel, the longer the non-propagating cracks that we found. So, also interesting data. This is the case of the medium carbon steel. We have the same crack length, just observing on the surface. We have the same crack length, non-propagating crack length for every defect. In this case was around 500, 497, 494, 486 and 512. So, the idea, these are some pictures of the fracture surface of cracks emanating from this defect, and the idea was to observe the shape of these non-propagating cracks at the synchrotron radiation facility in order to observe at the fatigue limit how is the condition of the crack on the root of the notch. So we bring the specimens from Japan to France, to Lyon, to inside the Lyon, and we cut a small specimen from the larger specimen containing the non-propagating crack. Here you can see this was a difficult process due, as you could see, the total length on the surface was like 500, the one that I show you, and this has to be smaller than 0.8 microns. So to identify the crack position and put we have some experimental difficulties. So we prepared the specimens and we took them to the ESRF. With this specimen, we pull from the specimen in order to open the crack, and we obtain the different 2000 radiographic projections, and then we obtain the 3D shape of these cracks. Regarding the tomography experiment, we were working with 60 keV, and the voxel size was 0.7 microns. High resolution. So this is what I had problem this morning to show. Let me see if we can have a look at the 3D shape of these cracks. Okay, maybe we are lucky. Just 1 second. Oh, apparently. Okay, then I will try. But the idea, these are the axial projections of the cracks. This is the 0 degree crack. This is the 30-degree defect, artificial defect, and this is the 60 degrees in the case of the low carbon steel. What we can see if on the set projection, if we see the sample from the top, is that the shape of these non-propagating cracks are really similar. We have a longer propagation on the surface and a smaller propagation on the notch root, but they are quite similar. And in case of the 60 degrees defects, we can see, if we see it in this direction, I don't know if you can see, but if we saw in the axis of the specimen, we can see that there are different cracks growing from the same initial defects. In this case, it's more clear. This medium carbon steel, the crack front is more with less roughness, and you can see also that from the drill hole, the final configuration of the three is really similar. We have some difference in the 60 degrees. Again, the 60 degrees defect. We have not much crack on the root of the notch. And finally, this is the higher mechanical properties material, the low alloy steel, and in this case we also can see that the non-propagating crack length diminish the size. The propagation is only 40 microns, and in the other case was almost 180 microns. And also we can see isolated cracks propagating in mode 1, in this case. Maybe I have more luck and we can see it. Sorry. Okay, this is the 0 degree 3D shape. It was really clear to find out where the crack it was. We had a good contrast level in order to identify where the crack ends. And we pull a lot also to, I want to show the 60 degrees, how these cracks are emanating. Sorry. Okay. And here you can see how these cracks start and act, they act completely separately one of the other. Maybe you can see it better in this image. And this was, I was saying this, that we have a good contrast level in order to identify where the cracks end, and the non-propagating cracks, so the measurement of these cracks made by optical microscope on the surface were almost the same as the measurements that we made on the tomography experiments, and the 3D analysis, the square root of area that we calculate seen from the top, follow the same tendency as the two-dimensional crack analysis. So, as some conclusions, as resumed, we did high-resolution, high-energy synchrotron tomography to find the 3D image with good contrast level that we can see where the crack is, and the 3D non-propagating cracks present the same tendency as the surface length analysis, and in case of 60 degrees tilted notches, the crack fronts appear to be much more discontinuous than in the 30 degrees and the 0 degrees. And what we are doing now is just extract from the 3D analysis. We are meshing these defects in order to do some stress intensity factor calculations. And the final thing that we want to explain is why we have this tendency of increasing the fatigue limit with the increasing tilting angle in case of the higher strength materials. That's it. Thank you.
Thank you.